good afternoon, everyone. Today I have a special pleasure to welcome Associate Professor Norman Waldberger from the School of Mathematics and Statistics at the University of New South Wales. Norman obtained his PhD from the Yale University, and he taught at the University of Stanford and Toronto before coming to University of New South Wales. Norman's research interests are diverse. They include lots of mathematical areas, including combinatorics, graph theory, geometry, foundations of mathematics, and others. Norman is, by self-admission, a YouTube enthusiast.
Fanatic, maybe.
Norman actually made over 550 YouTube videos on different interesting problems in mathematics. He has about 7,000 subscribers and over 1.5 million hits. So it's something for you to check after the talk, all these interesting videos. Now, Norman will tell us about more computational mathematics. So basically this talk will shake everything we know about mathematics. Please, Norman.
Well, thanks very much, Liliana, for that lovely introduction. I hope I can live up to it. Thank you all for coming. So I'm going to tell you a little bit about rational trigonometry, which is a new way of thinking about geometry and lays new foundations for geometry. But maybe I should say a few words beforehand. But I'm coming from a position of skepticism with regard to the foundations, the current foundations of mathematics. I believe that mathematics is actually on very shaky ground when it comes to infinite sets, when it comes to especially the continuum and the nature of the continuum and the usage of so-called real numbers, which in my view are best described as unreal numbers rather than real numbers. And as people who are computer-oriented, I think you can probably appreciate that there's a rather big gulf between pure mathematics and computational computer science in terms of how you can actually implement the theories of the pure mathematics. In particular, when it just comes to representing real numbers is always a major challenge, and it's a difficulty that I think is due mostly from the pure math side, that we are faking it when it comes to real numbers. And so the question is, how do we put up some alternatives? So I want to show you today some alternative ways of thinking about things. So please leave your thoughts about real numbers behind just for an hour. And let's suppose that you more or less only knew about the rational numbers, which from my point of view is the proper foundation for mathematics on which we build a solid, clear, and logical mathematics. Okay, so let's start with two familiar triangles looked at in a different way. Okay, so this is the usual 90-45-45 triangle, but you see that I've described it in terms of, instead of having an angle of 45 there, or perhaps pi over 4, there's a number a half. And this is 1 and that's 1, but this, instead of being root 2, it's 2. And instead of the area being whatever it usually is, I guess half, there's something called 4 there. This over here is, of course, also the sort of the second situation that undergraduates know about. The 1, 2, root 3 triangle that we all learn. But instead here we have 3/4, and actually if we split this one up here, there would be a spread of 1/4 there, and the quadri of 3. So this is the start of rational trigonometry, where we're replacing distances and angles with new notions called quadrants and spread, and replacing area with essentially its square called quadria. Okay, so this was developed in 2005 in my book, and it leads to many new things. It leads to metrical geometry with a general bilinear form, very general approach to geometry. It leads to new understandings of relativistic geometry, a remarkable threefold aspect of planar geometries called chromogeometry that I hope to tell you at least briefly about today. It gives us a much more attractive and general approach to hyperbolic geometry and spherical or elliptic geometries. So these subjects become completely revolutionized by this point of view, but I'm probably not going to be able to tell you too much about them. But I will tell you a little bit. And what we're thinking about is to try to clearly separate the geometry of triangles from uniform motion around a circle. These two subjects these days are almost considered to be the same thing, but I say no, they're actually quite different. We do not need cosines and sines and tan and all those circular functions to study the geometry of a triangle. Okay, and then there's something called vector trigonometry, which leads to dynamics. But I guess the real killer application is that this point of view brings into possibility the idea of dramatically simplifying high school maths education. So I claim that if we look at things in the right way, things become dramatically simpler. And you will see some of that in today's talk. Okay, so I'm going to start with the basis of linear algebra. So we'll just assume we know a little bit about linear algebra. We're going to start with a dot product or inner product on a two-dimensional vector space. And if you like, you can think about the usual dot product given by x1, x2 plus y1, y2. But what I'm going to say also works for a relativistic dot product that you might get by replacing the plus sign with a minus sign. And we might also be considering an analogous thing in 3 dimensions, the usual inner product. Okay, so our starting point is we have a vector space with an inner product, and our first definition is the quadrants of a vector is just v dot v. That's the simplest thing you could do. The quadrants between points is the quadrants of the associated vector. So we're talking about the sum of the squares of the coordinates. And we're going to avoid taking square roots if we can. So that's quadrants between vectors. So now there are 2 very important theorems. The 2 most important theorems in geometry, in my opinion. The first is Pythagoras' theorem, which is now restated in a form much more in line with the way Euclid presented it, that if we have a triangle like this, then we have perpendicularity there precisely when q1 plus q2 equals q3. This is my notation for quadrants. I put a little bit of rectangle there so we know we're talking about quadrants and not distance. Okay? And geometrically, of course, those quadrants really are representing the area of a square. All right, so that's Pythagoras' theorem, which we all know. Here's perhaps a result that you don't know. That if the 3 points don't form a right triangle, but rather form a collinear set of points, then the 3 quadrants that they form have a relation. It is this relation. q1 plus q2 plus q3 squared equals 2 times q1 squared plus q2 squared plus q3 squared. Now you could obtain this simply enough by saying, well, in terms of distances, d1 plus d2 equals d3. Or maybe d1 plus d3 equals d2, depending on the orientation of the 3 points. If you try to convert that into a relation between the squares of the distances, you will find this relation here. And it's an interesting exercise to do that. The formula is obviously symmetric and shows that the asymmetry involved in the distance formulation disappears with this quadratic formulation. So it's an interesting exercise. I'm not going to prove that. I want to rather go to the analog of an angle. Okay, we're going to replace angles with a more rational notion here. So if we have 2 vectors v and w, we're going to define the spread between them in terms of the dot product by the following crucial formula. The spread between v and w is 1 minus v dot w squared over the quadrants of v times the quadrants of w. Or in terms of the dot product, just like this. Now you will be used to, if you've done linear algebra, to not have the 1 minus here, just to look at this thing and to take its square root, and then apply some strange inverse circular function called cos inverse to obtain a so-called angle. And the reason that you do that very complicated thing is so that when you have 3 like this, if this is an angle of 4 and this is an angle of 5, then the whole thing is an angle of 9. The whole thing is built so that you're forcing that linearity on this situation. I say that the linearity does not really want to be there. Okay, the linearity does not want to be there. It wants to be this. This is the algebraic reformulation of it. In terms of the usual inner product, it's directly like this, and then there's a famous identity that goes back to Fibonacci, maybe even Diophantus. It allows you to rewrite this way. And we recognize this, the square of the sine of an angle if you did know what an angle and sine were. Here's a spread protractor that you can find on the internet. And you can see it's not quite linear because this is not an angle. It goes from 0 to 1. Half corresponds to 45 degrees. 30 degrees is a quarter. 60 degrees is 3/4. And it's symmetric on this side. Okay, this formula shows that the spread can be also interpreted as the ratio of a determinant squared divided by the product of the quadrances. So it's really just a normalized determinant. You've got these two vectors. You take the area of the parallelogram that they form. You square that so that it's invariant under interchange. And then you normalize so that it's independent of the size of the vectors. It's really the simplest thing you could do, really, if you had to start all over, to be quite honest. Okay, that's the spread between two lines. And it's really between two lines and not between two rays. Two lines. It takes some getting used to. Now, one of the great things about putting up YouTube videos is I have a lot of correspondence with people all over the world. And I get some interesting comments. And in particular, sometimes I learn something that's very valuable. And this is a great example. So Paul Miller of the Isle of Wight discovered the following dramatically simple way of thinking about what a spread is. Okay? He said what we do is we just take an ordinary protractor, but we forget about the inscriptions. It's really just a semicircle. And we take this line here and say another line here, and we're interested in what the spread is. Okay? So what you do, you see where you put the vertex here at this endpoint. You see where the line intersects the semicircle, and you drop a perpendicular down, where there happens to be a linear scale from 0 to 1. A little bit of elementary geometry will convince you that that position is sine squared of that angle. In other words, that position right there, which is 0.14, is the spread between this line and this line. Fabulous. And it shows just how elementary and natural this notion of spread really is. Okay, this is simpler than an ordinary protractor, because to make an ordinary protractor, you have to divide this thing up into 90 or pi or whatever it is you're interested in. And dividing a semicircle up into even pieces is not at all easy. This does not require a prior subdivision of the circle. All right, so what can we do with these things? Well, here then are the main laws of trigonometry with quadrants and spread instead of distance and angle. They relate to a general triangle with 3 quadrances, Q1, Q2, and Q3, and 3 spreads, S1, S2, and S3. And these laws will be familiar to you in some form. They will look familiar, but they're actually independent of anything else that you know. And in fact, I'm going to prove them shortly for you just from the definitions that I've given you. So there's the cross law, which says that if you know 3 quadrances, you can find the third spread, or any one of the spreads, by Q1 plus Q2 minus Q3 squared equals 4Q1 Q2 times 1 minus S3. The spread law, which is obviously analogous to the sine law, is S1 over Q1 equals S2 over Q2 equals S3 over Q3. And this biggest and most interesting law, the triple spread formula, says that there's a relationship between the 3 spreads of the triangle. The relationship is S1 plus S2 plus S3 squared equals 2 times S1 squared plus S2 squared plus S3 squared plus 4 S1, S2, S3. If without this term here, that's exactly the triple quad formula that I talked about earlier in terms of 3 collinear points. So if you remember that formula, you just add this little cubic term to get the triple spread formula. And this is the analog of the result that you know as this angle plus this angle plus this angle equals, hang on a second. 3.1415926. Well, that's as far as my calculator goes. But it does keep on going. People say, well, isn't this a lot harder than the sum of angles? No, it's a lot easier because we avoid all the complexity with pi. Pi is great, but we're avoiding it here. Okay, there's an easy consequence of Thales' theorem, which is interesting to remark. So here's the spread law. And if we consider a right triangle is a situation where one of the spreads is 1. Perpendicularity is 1. And in that case, we just immediately see that this spread here can be thought of as the ratio of opposite quadrants over hypotenuse quadrants. And similarly for this one. And then Pythagoras' theorem takes the form S1 plus S2 equals 1. So instead of adding up to 90 or whatever, they add up to 1 in a right triangle. Okay, and this also gives sort of a high school or a public school interpretation of what the spread is. It's opposite over hypotenuse, but it's opposite quadrants over hypotenuse quadrants. It's a number, not a function. All right, so let's apply this to the Zohm construction system, which I presume you've all seen. These are little construction kits that make all kinds of beautiful three-dimensional models. And it comes in 3 blue and 3 red and 3 yellow struts. And you can make all kinds of pleasant things. And I just want to show you that with this technology, we can describe real-life situations in ways that we really can't with angles and lengths. So, okay, there's some... there's some numbers here, beta and tau, which I'm not telling you what they are. I think they're probably below my page. Okay, there's beta at least. Beta is 5 plus root 5 on 8, and I think tau is 1 plus root 5 on 2 squared. And it doesn't really matter. The point is that we can calculate, these are the quadrances of the 3 lengths of the various things. And then with some playing around with the various laws, we can study all kinds of configurations. For example, there's a pentagon. It ends up having spreads of alphas and betas prominently around. Instead of 36 and 72s and so on, we end up with these alphas and betas, which do have root 5s in them. Okay, so it's not entirely rational. We don't mind going to a quadratic extension occasionally. And we can study all kinds of triangles very explicitly and make computations and actually get actual real correct values for things. So for example, for this triangle that you can make, the spread here is 2/3, here it's 2/3, here it's 8/9. It's very concrete things, and often you get rational numbers, or occasionally you get some things involving, there's the tau, some quadratic irrationalities perhaps. Okay, those are some more triangles that you can make with Zohm. That's basically a list of all the primitive triangles. Okay, now I want to prove these 3 laws that I told you about. Right? I told you these 3 main laws of trigonometry. I want to now spend about 5 minutes proving them, essentially from scratch, without any knowledge of circular functions or any geometry really. I'm just going to use a bit of linear algebra. All right, so the first law is the cross law, which I remind you is this is what we're aiming for. It's the relationship between 3 quadrances and 1 spread, say S3. All right, let's look at Q3. What is that? That's the quadrants of this thing. That's the quadrants of the vector A1, A2. The vector A1, A2 can be thought of as the difference between A3, A2 and A3, A1. A3, A2 and A3, A1. So the definition of quadrants is this vector dotted with this one. Now we're only going to use the symmetric nature and the linearity of the bilinear form. So when we expand this out, this is A3, A2 dotted with itself. That is Q1 by definition. The A3, A1 dotted with A3, A1 is by definition Q2. And we get minus twice the dot product between these two things. Okay, and now what is the definition of S3? The definition is it's 1 minus the dot product between these two vectors divided by their quadrances. Okay, we've just established what this is. From here, we can replace this with Q1 plus Q2 minus Q3. And there's a 2. Squared was a 4. And then we just multiply by Q1, Q2. And we get, bring the 1 and the S3 on the other side, and we get this thing here immediately. So that contains all the information of the cosine law. In fact, it's stronger than the cosine law in that it allows you to do accurate calculations without having to use a calculator and drop decimals. If you're willing to work algebraically, there's no loss of information. Okay, that's our first of the 3 laws. Now here's the second one, which is the spread law, that's relationships between spreads and opposite quadrances. Okay, there's the cross law that we've just proven. Let's bring the 4q1, q2, s3 term to the other side, and notice that the remainder can be rewritten via an identity into this form. That's just an identity going from here to here. This is actually a very important concept. We've seen this thing in the triple quad formula with 3 collinear points. It's the difference between the left and right-hand sides in that formula. So let's give it a name. Let's call it the quadri of the triangle. I'll say a little bit more about it in a second. But to continue, so now what we observe, this is symmetric in Q1, Q2, and Q3. So that this quantity here has to be the same as 4q1, q3, s2, has to be the same as 4q2, s3, s1. And then when we divide by the product of the 4q1, q2, q3s, we get the spread law. So contained here is a rational form of Heron's formula. If you know the 3 quadrances of a triangle, how do you find its area? Heron's formula, you may know, has a lot of distances and square roots. Right? This is a much superior form. I call it Archimedes' formula because Archimedes probably knew Heron's formula before Heron did. All right, so Archimedes' formula is that this quantity here is really 16 times the square of the area. So if you have to calculate the area from the 3 sides of the triangle, please use this fact and not the usual one. Okay, we've proven the spread law. There's only one more to go, and then we will have established the basis of trigonometry. And we'll be ready to go out and do all those engineering problems and surveying problems. All right, so the last one is this one here, the triple spread formula. How are we going to prove that? We're going to combine the 2 ones that we've already just proven. We're going to combine the spread law that we've just proven and the cross law that we've proven. So let's call this common ratio 1 over d. I don't care what d is, it's just some number that allows me to write q1 as d times s1, and q2 is d times s2, and q3 is d times s3. And then I'm going to substitute those into the cross law so that all the q's disappear and we just get an expression involving s's and some d's. But pleasantly, the d's appear with power 2 on this side and on this side, so they cancel. And we're left just with a relation between the 3 spreads of the triangle. There. And then if you want to, you can expand that out and get this one. So that's the basis of rational trigonometry, and it provides, I think, an interesting alternative to the months, maybe years of work that high school students have to learn to do ordinary trigonometry. Circles, cosine, sine, secant, all these irrelevant things. Okay. These 3 laws, or actually them together with the Pythagoras and the triple quad formula, those 5 laws altogether, allow you to solve the majority of trigonometric problems. And I invite you to test that out next time you have a trig problem. There's nothing like doing it yourself to see. You'll probably be amazed. You'll go, wow, this works very smoothly. It's surprising. So I've done hundreds of these things, so I've been surprised many times, but it's now getting commonplace to me. But if you haven't, it's something to look forward to. You can try it out. Okay, there's a few consequences that lead to some interesting connections with special functions that I want to tell you about now. Okay, and the results basically, I guess, starting from this this theorem here. What happens if you have two equal spreads? So let's go here. If we have a spread of S and another spread of S, what's the combined spread? Well, it's not linear. It's not 2 times S. Okay, this is not an angle. It's something else. How do we figure it out? Well, we have to use the triple spread formula. So to calculate that spread, and notice my notation for spreads. Notice also that I don't care where in the 4 possible positions that little line goes. Okay. So why is it the triple spread formula? Well, if I imagine just moving that line over a little bit, then you can see that it's the same as that triangle there. So those 3 numbers, S, S, and R, have to satisfy the triple spread formula. All right, so plug it into the triple spread formula. Reduce. You find that it factors. So you find that R is either equal to 0 or it's equal to 4 times S times 1 minus S. Now, this is a very famous function. This is the logistic map, which looks like this. It's important in chaos theory. It's a nice little parabola that fits exactly in the box of height and width 1. It just goes right up there and touches that box and comes back down. All right, so that makes us want to ask, what happens if we do it again? What happens if we put 3 spreads together and ask what's the combined spread? You're going to get a polynomial in S. That polynomial is called the spread polynomial. And, okay, so here's various examples. I guess these are repeated, I don't know why. I guess that's maybe the 4th one, that's the 5th one. Here's a whole bunch of them. So that's S2, that's S1 first of all, that's S2, and then S3, I guess that'd be S3. No, S3 goes like this. And then S4 and S5. Okay. They all bounce around in the box, the 1 by 1 box. Now, if you know about the Chebyshev polynomials, you'll know that the Chebyshev polynomials do the same kind of thing. So is there a relationship between these and the Chebyshev polynomials? Yes, there is. So it's the relation here. So the spread polynomial is really an affine shift of the spread of the Chebyshev polynomial. Tn is the usual Chebyshev polynomial. So to transform it from the -1 to 1 square to the 0, 1 square. And here are some other formulas for them. There's more in my book. Mike Hirschhorn computed the generating function for me. So you might think, well, okay, these are just like Chebyshev polynomials. What's the difference? Well, it turns out that there's a remarkable difference. Okay, first of all, let me just exhibit some of them. So here's some spread polynomials. S0, S1, S2, S3, S4, S5, S6, S7. And there's nice patterns with the coefficients and so on. But here's the really remarkable thing about these things. That the spread polynomials enjoy this incredible factorization property that the Chebyshev polynomials don't. So some number theory comes into view that we don't see with the Chebyshev polynomials, even though they're just affine shifts. It is this. So this was discovered by my student, Shuxiang Go. Is that the nth spread polynomial is actually a product over all k dividing n of some other polynomials phi sub k of s. These other polynomials are independent of n. They're just God-given polynomials. So phi 1 happens to be s, phi 3 is this one, phi 5 is this one, 7, 2, 4, 6, 8. There's a list of these things. So for example, if you want to calculate S12, S12 happens to be phi 1 times phi 2 times phi 3 times phi 4 times phi 6 times phi 12. What's the pattern behind these? We've stared at these for a long time. There's lots of interesting patterns, but it defies easy control. It's hard to understand what's happening with these phi polynomials very easily. I think it's going to be a very rich subject of investigation in sort of the land of orthogonal polynomials. Okay? So if you want to work on some virgin territory, stare at those polynomials and figure out what's going on with them. Okay, so I'm going to mention a few other things that happen. So if you have 3 points in on a line, 1, 2, 3, then we've already said that the 3 quadrances obey the triple quad formula. What happens if you have 1, 2, 3, 4 points on a line? And we consider quadrants Q1, Q2, Q3, and Q4, back to the first one. Okay, well, this is the relation. So that polynomial is the one that determines the relationship between 4 collinear points. And then the other two quadrances that we haven't talked about can be expressed in rational functions in terms of the quadrances that we know. There's a corresponding thing if you have 4 lines. If you have 4 lines, you can talk about the spread S1, spread S2, spread S3, and then the spread S4 back to the first one, and ask what's the relationship between those 4. There's the answer. Okay, it's given by this more intimidating relation. So this function R, A, B, C, D, it controls 4 collinear points. And then the other the other spreads between 1 and 3 and 2 and 4 are given by these rational functions. What happens with 5 points? Well, I know that there's a relation, and I sort of know what degree it is, and I've written it down in some form, but I haven't written it down in a reasonably nice form like that. And I don't really know how to write down the higher ones. So that's a pretty fundamental thing. You have, say, 5 points on a line, 5 cyclical quadrances. What's the possible relation? Or correspondingly with spreads. It turns out that remarkably those linear things also somehow influence higher dimensional things. In particular, if we're looking at a cyclic quadrilateral, so here's a cyclic quadrilateral, and okay, so we have these quadrances, say Q1, 2, Q2, 3, and so on, and then we have spreads subtended by them. So if you have a chord on a circle, then you know from classical trigonometry that if you have a point on the circle and you're looking at that chord, that angle is usually constant. I say usually because it's not quite, because it's constant if the point is on this side, but if the point switches to this side, then the angle changes. It's one of those small embarrassments that working with angles gives you, that you just usually say, oh, that's the way life is, you know. But it's because the angles are the wrong notion. The correct theorem is that the spread subtended by a chord is always constant. That's true no matter where you are on the circle. All right, so that chord subtends a spread. Let's call it R12. So that would be that spread is R12. That's R12. Okay, so then we have this theorem anyway, that same R function that I was just telling you about controls the relationship between these 4 spreads in a cyclic quadrilateral. Okay, let's do a 3-dimensional application. So this is supposed to be a right tetrahedron. That is, it's a tetrahedron which has 3 right lines meeting at one vertex there. All right? So the base is a right triangle, and these are also right triangles. And I've labeled these quadrants as Q3, Q1, Q2 along the base. The height quadrants will be H. And let's consider these two spreads along these two sort of sides, R1, R2. And let's also consider the spread S up here between this side and this side. All right, so here's some sort of typical kind of calculation that because this is a right triangle, Q3 has to be Q1 plus Q2 from Pythagoras. Similarly, because we have right triangles here, the quadrants between A1 and B will be Q2 plus H, and the quadrants between A2 and B will be Q1 plus H. So in this big triangle, A1, A2, B, the three quadrants are Q3, this thing, and this thing. And the spread up here is S. So the cross law applied to that is that Q1 plus H plus Q2 plus H minus Q1 plus Q2 squared will be 4 times Q1 plus H times Q2 plus H times 1 minus S. Well, pleasantly, this side simplifies, and we just get a 2H squared. And then when we divide this, we get that 1 minus S equals H over Q1 plus H times H over Q2 plus H. And these ratios exactly are the ratios defining the spreads R1 and R2. Because H over Q1 plus H is opposite over hypotenuse in this triangle here. So we're getting 1 minus S equals R1, R2. So we've established a relationship in this tetrahedron that the spread up here is, well, 1 minus it, is the product of these spreads here, independent of any of the other quadrances and the shapes of those triangles. Okay, this leads to a very important theorem, so I'm going to restate what I just said. Okay, that same configuration. But instead of looking at R1 and R2 down here, I'm going to look at the opposite quadrants spreads, rather, and call them Q1 and Q2 up here. Okay, we saw that when you have a right triangle and one spread is S, the other one's going to be 1 minus S. That was Pythagoras in terms of spreads. So we know that Q1 up here is actually 1 minus R1, and Q2 is 1 minus R2. So that previous relation I just established can be rewritten as 1 minus Q1 times 1 minus Q2. And that leads to what I think is one of the most important formulas in mathematics. Okay? It is the projective Pythagoras' theorem. What is that? It's a theorem that relates to a projective triangle, a right projective triangle. So the triangle here is now the tripod formed by these 3 lines emanating from O. We have 3 lines emanating from O. And those 3 lines, well, they sort of form a right tripod, like 2 of the sides are perpendicular. And then the other quantities are the spreads, spread Q1, Q2, and Q3. And the relation is a lot like the planar Pythagoras, except there's this additional quadratic modification. Okay, this turns out to be a fundamental formula in spherical trigonometry and in hyperbolic geometry. It has huge repercussions, but we can see it as well, I've already proven it here now for you. You can see why it's true. It just follows from elementary considerations from a tetrahedron using just what we've done. Okay, it's a very, very fundamental formula. It's equivalent, if you know some spherical trigonometry, it's easily equivalent to the usual Pythagorean theorem in spherical trigonometry with cosines and sines, but we're stripping away all that transcendental stuff and just getting at the algebraic heart of the matter. Okay, so in that direction, there is this projective point of view. Maybe I won't say that much about that. I will just, okay, I'll say one thing about it. Suppose you have 3 lines emanating from the origin, thanks, and you're interested in sort of 3-dimensional geometry, maybe doing robotics or graphics or something, and you want to understand that triangle. Okay, so if you have 3 lines emanating from the origin, then there are 6 natural quantities associated to that triangle. What are they? Well, any 2 of them make a spread. Usually we would say angle, but we prefer to say spread. So any 2 lines have a spread. So there are 3 of those. And then any 2 planes of that projective triangle also have a spread between them. So algebraically, we can define those things in terms of the same formula that we use to define spread. 1 minus dot product squared divided by quadrants times quadrants. But pleasantly, we can use essentially the same form for the dual thing for defining the spread between 2 planes, because essentially we just use the normals to those planes to define the spreads. Okay, so then you get you have a projective triangle. Instead of drawing it like this, which ends up being a little bit cumbersome, you can think of it on the surface of the sphere if you like. Okay, I'm going to use a slightly opposite notation from what I do in the planar case. So instead of talking about spreads as being small, they'll be capitalized in this situation, and the quadrances will be small instead of capital. Okay, that's just to alert us that we're talking about the projective situation rather than the affine situation I was talking about earlier. All right, so we can represent that a little bit easier like this, and we can just strip away the origin and just talk about the triangle itself diagrammatically like this. And we can still ask the same relation. What is the relationship between these 6 numbers? So these are the formulas of spherical trigonometry that they study in astronomy, but now recast in this rational language. So there are no sines and cosines or tans or anything like that, obviously. Okay, it's all rational things. So the relations are that, well, there's the projective spread law, S1 over Q1 equals S2 over Q2 equals S3 over Q3. And then we have, in addition, projective versions of the cross law. So it's a little bit more complicated. S3 Q1 Q2 minus Q1 minus Q2 minus Q3 plus 2 squared is 4 times 1 minus Q1, 1 minus Q2, and 1 minus Q3. And there's a dual version because this situation has a duality that's not there in the planar case. There's the dual situation where you just replace the projective quadrances with the projective spreads. Okay, so there's an interesting notion that now arises that analogous to the quadria of the triangle in the planar situation, we now have a notion of projective quadria, which is interpreted as the solid spread. So if you have a tripod in space, there's a solid spread which plays the role of the solid angle, replaces the solid angle in 3-dimensional computations. Okay. And it's given by, so the solid spread would be this spread S1 times 2 adjacent quadrances. That's symmetrical along most things. And it's interpreted, you can interpret it in terms of altitude quadrances if you like. I just want to show you some formulas, some pictures really of what it looks like in practice if we start analyzing some simple tetrahedra. So here's a tetrahedron made with Zohm. It's a purely right tetrahedron there, 1, 1, 1, and 2, 2, 2. Okay, so you can determine the face quadrias. That's just a planar situation. And now we can talk about the edge dihedral spreads, the spreads between 2 faces that meet at an edge. And well, these ones are 1 here, but the edge spreads along these green edges are 2/3. That's the spread between the 2 planes that meet along those lines. And the solid spreads that I told you about, there's a solid spread of 1 here, and at each one of these, there's a solid spread of 1/4. Okay, I won't mention that. Then the regular tetrahedron, so the analog of an equilateral triangle. All the quadrances are 1, so the face spreads are just all 3/4. That's the analog of 60 degrees. The edge spreads are interestingly 8/9. 8/9. And we've seen 8/9 before. Once in one of my earlier things, I showed you something with 8/9. So this is actually something that's interesting to a chemist because it's sort of angled in a, I don't know, benzene molecule or something. But this number of 8/9 appears very naturally here in the geometry of this tetrahedron. I think this is very attractive, and it somehow leads us to this idea that maybe in three-dimensional space there are all these interesting numbers that are invisible to us currently. I mean, we can measure all kinds of things, and if you measure anything with an angle, of course you're going to get 33.79452 ... and it's not going to mean anything to you. But here the possibility emerges of doing everything rationally and getting rational numbers, or maybe close to rational numbers that actually have content and that are correct. I want to tell you, just to finish, one more thing about 8/9, and for that I wonder if I can borrow a piece of A4 paper from someone. Can I borrow a piece of paper? All right, so this is a piece of A4 paper that you all know, right? And the A system has the property that when you fold it like this, you're getting a shape which is similar to the one you started with. That's the defining property of the A system. All right, so this is A4. So what are the quadrances? Well, that relation I just told you implies that in ordinary usage that would be 1 and square root of 2. But we now have graduated to doing things with rational trigonometry. So this is 1 quadrant, and this is a quadrant of 2, which means that this diagonal is a quadrant of 3. Okay, so let's, can I borrow your pen? Let me just borrow that for a second. Thank you. All right, so here's a diagonal. Here's a diagonal of our A4. What is this spread here? Well, that was 1, and that was 2, and that was 3. So that's going to be opposite over hypotenuse, so that's 1/3. Yeah? And if you put if I had another one and to put it on top of it, just reflected it like this. So imagine having one diagonal and then another diagonal coming up there. I would have 1/3 here and another 1/3. So to compute the cumulative spread, I would have to use the logistic map. Right? I do not multiply by 2. I have to use the formula 4 times s times 1 minus s. All right, so if s is 1/3, what do we get? We get 4 times 1/3 times 1 minus s, or 2/3. We get 8/9. So that same spread is pretty close to being visible to you with an A4 paper next time you look at it. That spread of 8/9. The same spread that's occurring here between the faces of this regular tetrahedron. All right, so there are many other applications of this this business, and it's described in my book, Divine Proportions, and I have a few copies to give away here, so if any of you would like a copy, I invite you to come and get a copy after the talk. I don't have that many, but a few. All right, so thanks for your attention.
Thank you very much. Are there any questions for Norman? Yes. Brendan, first.
Oh, well, what did pi ever do to you?
No, I like pie, but...
And What's your intentions with this? Is this to revolutionize education, or is it?
I think that's would be the best thing. Yeah, I mean, I think I want mathematicians to think more carefully about the foundations of their subject, and one of the reasons they've been avoiding doing that is because they don't know what to replace the current theory with. So I'm giving them an alternative, saying, all right, you can abandon the waffling and still do mathematics, and it's often a more beautiful and natural thing that results. But I'm very interested in mathematics education. I think we have to do something to help young people, and the current mathematics that we teach them is just too complicated. Logically, trigonometry is a very complicated subject that logically requires calculus before you understand it. It's a cheat to pretend that these students can logically follow trigonometry if they haven't done calculus. So I want to fix education.
So your metric, that doesn't have to be positive definite all the time.
Yes, all the formulas work even if it's a not positive definite inner product, in particular a relativistic one. So all these formulas also apply to relativistic geometry.
And the spread formula, it seemed to me related to the projection formula of a vector onto another vector. Is it?
The spread, which one? The
combination of the spread. It seemed to be something related to the projection of one vector onto another vector, and then taking the unit product of that projection.
Yeah. There's all these relations. Yeah, there's all these relations. But so projection works very naturally in this setting. Yep.
Any other questions?
Yes.
So you'll have to keep me, I'm an engineer, so I don't know the proper term for it, but trigonometric functions,
Yep.
with wireless and everything, are they re-expressed in this kind of notation and all that kind of thing?
So what I would like to do is encourage people to change their notation or their terminology a bit. I prefer that people call them circular functions, because in my view they're properly associated with the geometry of a circle, and in particular uniform motion around a circle. For that, the cosine and sines and the circular functions are indispensable, no question. What I want to do is I want to clearly separate that circular business from the linear business of triangle geometry. So I'm not saying cosines and sines are not important and they don't have a role. I'm saying they have an important role whenever you're doing anything that has to do with uniform motion around a circle.
You may have just answered my question, that rational trigonometry seems to make a lot of things simpler. What kind of things have you found where the opposite is happening?
Okay, so the best examples of things where rational trigonometry doesn't work so well are when you have an angle chasing problem. Sometimes if you presented a problem where you have to chase angles, then rational trigonometry becomes much more cumbersome. But generally speaking, those problems don't rise naturally so often, and usually they're just in simple cases. The other difficulty with rational trigonometry is that you saw the algebraic complexity when we went from 3 points to 4 points to 5 points. This is a fact of life, that algebraically things get exponentially, or not power-wise, more complicated with the more the number of points you have. That's a fact of life, but it becomes evident when you're doing rational trigonometry.
Joe, you had a question?
Yeah, I did. I got distracted with your answer to that question about circular motion, and I started thinking about planetary motion, because the causes and sines are very important in elliptical functions and ellipses as well. But if you're looking at the confluence of planets, say, then you're talking about triangles, but you're talking about things moving in elliptical paths. So you can't get away from the circular trigonometry.
Yes, I agree. So for astronomical applications, which are ultimately very closely related to uniform motions around circular uniform motions, the circular functions are actually indispensable, for sure.
Right. And as a follow-up question, can I ask you, have you tried the same thing with the golden ratio?
Well, the golden ratio sort of appears in the geometry of the pentagon. It gets, in order to create a pentagon, you need a square root of 5 in your system, one way or the other. And so the golden ratio naturally plays a role whenever you're dealing with fivefold symmetry.
Yeah, your tau and beta parameters reminded me of that one.
Yeah, they're very closely connected with their golden ratio. Tau, I think, was just the golden ratio squared. Yeah.
Another question, please?
Well, what's your YouTube channel name?
Well, my username is NJ Wildberger, and the channel name is Insights into Mathematics.
Okay.
But if you Google rational trigonometry, you will get to it.
Any other questions? Okay, please join me in thanking Norman again.
Thank you.